We are usually taught that stars burn in splendid isolation, forging their fates across billions of years in the silent vacuum of space. But right now in the constellation Orion, that comforting rule has been violently overturned. Betelgeuse is not merely a radiant red supergiant. It is a behemoth so immense that if it replaced our Sun, its swollen outer layers would stretch beyond the orbit of Jupiter. For generations, we regarded it as a solitary colossus. We were wrong. Astronomers have now gathered decisive evidence of a companion star, similar in mass to our own Sun, locked in its deadly embrace. Yet this companion does not circle safely in open space. It is orbiting deep inside Betelgeuse itself. The smaller star is literally carving through the supergiant's outer atmosphere, slamming against the gas and forging a turbulent trail of upheaval. This is the Siwarha event. Systems like this captivate us because of what hides in the subtle signals, the faint shifts in light and motion that expose a far more dramatic reality. We often think of the stars as timeless, unchanging points of light, fixed for millions of years. This idea holds for most stars, but Betelgeuse has always defied it. Long before telescopes existed, ancient sky watchers noticed this star's restless nature. It did not simply shine steadily. It transformed. The earliest records come from oral traditions of indigenous peoples in Australia's Great Victoria Desert. Their stories portray the figure we call Orion as a hunter chasing a group of sisters, represented by the Pleiades cluster. In those tales, the brightness of the hunter's right shoulder, exactly where Betelgeuse sits, rises and falls over time. The legend describes the hunter filling his hand with fiery power to strike, only for the eldest sister to push back with her own magic, causing the glow to fade. This is an unbroken observational record of the star's pulsation cycle, captured thousands of years before modern science arrived. It shows the star has been swelling and contracting violently for as long as humans have gazed upward. We also possess written accounts hinting that the star altered color across recorded history. In the 1st century BC, court astronomers in ancient China noted its hue as yellowish. Just 2 centuries later, Greek observers described the same star as distinctly ruddy. That transition from yellow to red matches precisely what happens when a star evolves into a red supergiant. Its surface cools as it expands, shifting its light toward the red end of the spectrum. These early witnesses were likely recording the final stages of Betelgeuse settling into its current bloated form. Systematic scientific monitoring began in the 19th century when an English astronomer recorded Betelgeuse briefly outshining the usually brighter blue star at Orion's foot. This was the first quantified proof of variability. The star was not merely changing over centuries, but over months and years. It was breathing. By the early 20th century, astronomers accepted it as a semi-regular variable star whose brightness rose and fell on its own rhythm. Yet as measurements sharpened, the rhythm refused to make sense. The pattern grew too intricate for a single star acting alone. By the mid-20th century, enough data existed to plot the light curve over decades. The graph showed chaos rather than a clean wave. Mathematical decomposition, however, revealed 2 hidden rhythms. The first was familiar, a primary pulsation repeating roughly every 400 days. We understand this cycle through the Kappa mechanism, layers of gas inside the star turning opaque when heated, trapping energy like a pressure cooker, forcing expansion, then cooling and shrinking again. This is the labored breathing of a dying supergiant. If the 400-day cycle stood alone, the puzzle would have been solved long ago. But the data revealed a second, far stronger and slower signal. The long secondary period, lasting about 2100 days, roughly 6 years. Every 6 years, Betelgeuse dims noticeably, then brightens again. This contradicted core principles of stellar physics. Pulsation periods tie directly to a star's density and mass. A 6-year cycle would require an impossibly diffuse structure that could barely hold together. The star could not be physically swelling and shrinking on such a timescale. Astronomers faced a genuine mystery. They needed a mechanism that dimmed the light on schedule without altering the star's size. They examined giant convection cells, enormous bubbles of hot plasma rising like boiling water, bright when ascending, dark when sinking. On Betelgeuse, a single cell can span the width of Mars's orbit. Yet convection is random. It cannot tick like a precise clock. Magnetic cycles similar to our sun's sunspots were considered next, but supergiant magnetic fields tend to be weak and disorganized, incapable of dimming the entire star so regularly. After eliminating every internal possibility, only one remained. Something external had to be at work. A strict repeating cycle pointed to gravity. It pointed to an orbit. The scientific consensus slowly shifted toward the idea that Betelgeuse was not alone. The 6-year rhythm was the gravitational fingerprint of a hidden companion. In late 2019, the star delivered a shock that upended years of careful study. It began to dim, not the usual gentle variation, but a steep plunge obvious even to casual skywatchers. By February 2020, Betelgeuse had faded to roughly 35% of normal brightness. For the first time in recorded history, Orion looked wrong. The red shoulder had all but vanished, now fainter than the other shoulder star. Public excitement surged. Many assumed the long-predicted supernova had arrived. The world waited for detonation. Yet high-resolution data from space and ground observatories painted a far less apocalyptic picture. The star had not exploded. It had merely sneezed. A colossal surface mass ejection hurled hot plasma outward. As the material cooled in space, it condensed into dark silicate dust, forming a thick cloud that temporarily veiled the star from our view. From Earth, we were watching Betelgeuse hide behind its own creation. The dust eventually thinned and the star recovered. This event proved a massive distraction, overlapping the 6-year cycle's minimum and deepening the data trough. Yet it also delivered an unexpected gift. Every telescope on the planet and in orbit turned toward Orion for months, yielding more high-quality observations than the previous 2 decades combined. Once the dust settled and supernova fever cooled, researchers returned to the persistent 6-year signal with fresh precision. For decades, the glaring brilliance of Betelgeuse, roughly 100,000 times the sun's luminosity, had hidden any companion. Spotting a sun-like star beside it was like trying to see a candle flame next to a searchlight. Astronomers stopped hunting for direct light and instead hunted for the disturbance it created. If a solar mass star plowed through the supergiant's atmosphere, it would leave unmistakable scars. They turned to interferometry, linking multiple telescopes into one virtual giant, and to high-resolution spectroscopy that dissected light for velocity signatures. The data showed no uniform spherical expansion expected from internal pulsation. Instead, they found a dipole pattern, one side of the atmosphere moving toward us, while the opposite side moved away. Rotation was ruled out. A star this enormous cannot spin that quickly without tearing itself apart. The only fit was external gravitational stirring. The companion was carving through the envelope like a spoon through soup, generating a bow shock ahead and a chaotic wake behind. We were not seeing the star itself. We were seeing the turbulent gas it left in its path. The 6-year dimming occurs precisely when this wake crosses our line of sight, blocking light with dust and density waves. Recent ultraviolet observations from space telescopes, sensitive to the hot outer layers, combined with ground-based precision data spanning nearly 8 years, have now delivered the first direct images of that expanding wake. The trail of disturbed material appears consistently shortly after the companion crosses our line of sight every 210 days. The companion generates ripples we can actually measure. With Betelgeuse still blocking a clear view, astronomers are preparing targeted observations for the companion's next emergence around 2027. This evidence has elevated the object from theory to confirmed reality. We now designate it Siwarha, Alpha Orionis b. Strong data indicate it is a main sequence star of roughly solar mass. Yet unlike our Sun, it does not glide through empty space. It swims inside a vast cloud of hot gas, millions of times less dense than water, but still thick enough to exert relentless drag. To grasp why this matters, we must revisit how orbits normally behave. In our solar system, Earth has circled the Sun for 4 billion years in near-perfect stability because space is a vacuum offering no friction. Momentum is conserved forever. Siwarha enjoys no such luxury. It orbits inside the red supergiant's outer envelope. Though tenuous, that gas creates dynamical friction. As the companion pushes gas aside, it piles up a denser wake behind it. That extra mass exerts backward gravitational pull, acting like a brake. Orbital energy bleeds away as heat and turbulence. The orbit decays. What begins as a stable path becomes a tightening spiral. Each revolution drops Siwarha slightly deeper. Denser gas means stronger drag. Stronger drag means faster energy loss. The process feeds on itself. Astronomers term this common envelope evolution, a brief, violent chapter in binary star life when one star engulfs the other. Usually we see only the aftermath in distant galaxies. Here, with Betelgeuse, we are witnessing the process unfold in real time right next door. The companion is trapped. Its orbit is decaying toward the core. As Siwarha spirals inward, the physics intensifies. Energy is never destroyed. It transforms. The orbital energy lost by the companion pours directly into Betelgeuse's envelope. Picture a blender blade spinning inside thick batter. The companion churns the gas, injecting heat and turbulence that puff the outer layers even larger and accelerate mass loss. This also explains a long-standing puzzle. Betelgeuse rotates far faster than a lone supergiant should. Simple expansion should slow rotation dramatically, yet measurements show surface speeds around 15 kilometers per second. The only viable source is angular momentum transferred from the spiraling companion. Siwarha is literally spinning Betelgeuse up as it dies. This rapid rotation stands as powerful evidence of ongoing engulfment. The mixing grows violent enough to unbind portions of the envelope, potentially ejecting huge shells of gas and forming a glowing nebula before the final plunge. The ultimate question is timing. Betelgeuse is already dying, its core fusing heavier elements in delicate balance. Siwarha is spiraling inward at an accelerating pace. Models based on current gas density and orbital speed project the merger completing within the next 10,000 years, to a star that is the blink of an eye. If Betelgeuse's entire life were scaled to a human lifetime of 80 years, this final act would last about 5 minutes. We have arrived at the climax. When Siwarha finally strikes the core, gravitational potential energy will unleash in a colossal burst. The impact alone could brighten the star dramatically, perhaps to daytime visibility, before any supernova. Astronomers call such events merger novae or red transients. False supernovae born when two stars become one. The deeper concern is whether this collision will trigger the true core collapse supernova. The core sits in precarious equilibrium. Sudden injection of mass and violent turbulence could shatter that balance instantly. Two main scenarios emerge from current theory. In the catalyst version, the merger sends shock waves racing inward, forcing premature collapse. The companion is swallowed and the star detonates almost simultaneously. In the quieter merger version, Betelgeuse absorbs the companion, emerging heavier, faster spinning, and slightly more stable, only to explode a few thousand years later. Distant supernovae already show fingerprints of recent mergers. Eating a companion may be a common final act for massive stars. The explosion we await could be the direct consequence of the drama unfolding now. The story of Betelgeuse has been rewritten. For millennia, humans saw only a lonely red giant slowly consuming its own fuel. The strange 6-year heartbeat was never an internal pulse at all. It was the footprint of a companion fighting for survival inside the monster's atmosphere. We solved the riddle not by staring at the star, but by tracing the wake it left behind. This revelation forces us to see the cosmos differently. The night sky looks frozen, yet it is a living drama playing out on timescales we can barely comprehend. If we could accelerate time, we would watch Orion as a motion picture, and right now we are witnessing its most intense scene, a slow-motion cosmic collision. Betelgeuse is not simply a future supernova candidate. It is a binary system caught in the act of self-consumption, a laboratory revealing how companions reshape stellar deaths. The process is violent, chaotic, and accelerating. Every glance at that red shoulder now carries deeper weight. Inside the calm orange light, a sun-like star is being eaten alive, churning the envelope and steering the giant toward its explosive end. The next time you step outside on a crisp winter night, look south toward Orion. Trace the 3 belt stars and lift your eyes to the bright red shoulder. It may appear serene, a steady beacon against the dark, but remember the truth hidden within that glow. A second star is trapped there, battling friction, spiraling ever closer, and forever altering the fate of the giant that engulfs it. What does this tell us about the hidden lives of stars we thought we understood? How many other cosmic giants are quietly consuming companions we have yet to notice? Drop your thoughts in the comments below. What surprises you most about this stellar drama? If these revelations from the universe light a fire in you, hit subscribe. Share this with fellow skywatchers who love the cosmos as much as you do, and keep looking up. The universe is far stranger and far more alive than we ever imagined.